heat capacity of a material is simply the energy required to raise the temperature of 1 kilogram of that material by 1 degree Celsius, and it's governed by this equation here. Delta E equals mc delta theta, where delta E means the energy transferred into or out of the system, m is the mass, C is the symbol for SHC, or specific heat capacity, and delta theta is the change in temperature. Now, if you're working out the specific heat capacity, you need to rearrange this equation in terms of C. Now, in this equation here, C is being multiplied by m and delta theta. To rearrange in terms of C so that C is on its own, it's the subject, you need to divide the other side by these values because you need to do the opposite. So here you can see that I've done that. C equals delta E divided by m delta theta. I've simply taken these two to the other side by dividing. Now, in an exam question, you could well be given all the values that you need to work this out straight away. But if you're working this out from an experiment, you probably won't have energy directly. You'll have some other values from which you need to work out the energy. Now, over here, I've got some values that I found experimentally to work out the SHC of some copper. You can see that I have a mass of 1 kilogram, a change in temperature of 20 degrees Celsius. I raised the temperature from 10 to 30 degrees C. And then I have 3 extra pieces of information here that aren't in the equation. I have a voltage of 9.6 volts, a current of 1.7 amps, and a time of 510 seconds. Now, generally, this experiment is done by heating the piece of material with an electrical heater. And to work out the energy supplied by that heater, you need to know these 3 things: the voltage and the current of the circuit, and the time for which the heater was run. Now, we work out the energy for this by using the 2 power equations, which are here. P equals IV and P equals E over T. Now, P equals IV means power equals current times voltage. P equals E over T means power equals energy over time. Now, if both of these are equal to power, then I can also say that they're equal to each other. IV equals E over T. Now, I know I, V and T for my experiment, and I want to know E to put it into this equation. So I need to rearrange this in terms of E. And all I need to do is get rid of this T on this side. Now, it's dividing on this side, so to move it to the other side, I need to move it up and multiply, which gives me E equals IV T. So I now have all the components of my final equation. I have C in terms of the specific heat capacity, and I now have energy in terms of what I know. I can combine these together, and all I need to do is put this term for energy into this equation here. So C equals IVT instead of the energy, divided by m delta theta. And I know all of these values. I need to put them into the equation, sub them in, and then work out the final value. So C equals current, which is 1.7, times voltage, which is 9.6, times time, which is 510, divided by m, which is 1 kilogram, and change in temperature, delta theta, which is 20 degrees C. Now, if I put all of these calculations into a calculator, it comes out of an answer of 416 joules per kilogram per degree Celsius. Now, the actual value for copper is 390 joules per kilogram per degree Celsius, but in an experiment, you're never going to get exactly the right value because some of the energy is wasted to the surroundings. However, this is still a really valid and proper way to work out the specific heat capacity of a material using an equation.